All right, right now we're taking on graphing quadratic functions with transformations. So the instructions here are to graph the quadratic parent function, then graph each of the following quadratic functions using transformations. All right, so first up we have y equals x squared. So here we see it's a quadratic parent function. We know what it looks like, right? This right side up U shape, right? We call it a parabola. So here, first off, I'm just going to remind you of what the parent looks like by making a table. So I'm going to use as my inputs, I'm going to use a -2, -1, 0, 1, and 2. So if I plug in a -2 and I square it, it becomes 4. If I plug in -1, right, as a quantity being squared, I get a +1. If I plug in a 0 and I square it, I get 0. If I plug in a 1 and I square it, I get 1. If I plug in a 2 and I square it, I get 4. So here is my parent function. It's the most basic structure I will ever see a quadratic function in. So here I'm going to start at the origin. There's my vertex. And then from my vertex, I'm going over 1 and up 1 on both sides, like so. Okay, I go back to my vertex, back to the origin, and I go over 2, and I go up 4. So right here, over 2 and up 4 right here. Okay, back to the origin where my vertex is. If I wanted another point, I could go over 3 and up 9, right? I'm just squaring the 3. Left 3 up 9, here would be another point. We usually just require those first 5. I'm just showing you how we could get more information. If I went over 4, I would be going up 16, right? However far I'm going over horizontally, I'm squaring that to find my distance going up vertically. Okay, let me connect my dots and make my parabola. Okay, my domain is always all of the values that x can take. So if I trace my function from left to right, I see, oh, well, it keeps growing left to right, so it is going to be all real numbers. I could also think about it as, what could I input in here for the x values? Well, I could plug in any number, square it to get the y values as my output. So my domain is all real numbers. I can write it like that. I could also use interval notation, and this would mean I would be saying negative infinity. I'm saying, well, from way over here would be negative infinity. Over to here, this extreme, positive infinity. Let me write that here just to see it clearly. We're saying it could be anything from this extreme to this extreme, negative to positive infinity. And then we always put the infinities into a soft bracket or parenthesis, just like so. That just implies that we're always approaching those two extremes. We're never exactly equal to those two extremes. So the infinities in interval notation always take a parenthesis or a soft bracket. Okay, the range. So here if I'm looking at it bottom up, the smallest value that y can take, my range is always the values that y can take. My smallest value right there is at the vertex with the y value of 0 or anything more than that. So I could write that as y is greater than or equal to 0. That's fine. If I wanted to switch to interval notation, I could say that the smallest value would be 0 and the largest one would be up here at infinity. Since it can be equal to 0, it takes a hard bracket. Infinity always takes a soft bracket or parenthesis like so. So either of these notations are perfectly fine. This is what we usually teach in Algebra 1. This is inequality notation. And then here we move on as you move up in math to interval notation, where we capture the two extremes, the low and the high. And if we can be equal to that value, it takes a hard bracket like so. And if we cannot be equal to that value, it takes a soft bracket or parenthesis. All right, so next it's recognizing the transformations and graphing accordingly. So here in this one we see, oh, the only thing that's different is this negative right here. So that negative is saying that it's a reflection over the x-axis. So it's the same as the parent, except it's not going to open up. It's going to open down. It's going to reflect over the x-axis. So when I graph it, I still start at the origin. Instead of going up, I'm going down. So as I would have gone over one and up one, instead of going up, I'm going down. So from that vertex, over one and down one, both sides, back to the vertex. Over 2 and down 4. Okay, if I wanted more points, I could go over 3 and down 9, just to be thorough. All right, so there is my quadratic function with a reflection over the x-axis. My domain, what can x be? Well, x can still be anything, so all real numbers. If I'm using interval notation, I could say from negative to positive infinity. My range, what can y be? Well, I'm reading it bottom up, so it could be negative infinity up until I get to 0 as the maximum value that y can take. So I can say that y is less than or equal to 0. I could use that notation. Or an interval notation, I can say from negative infinity up to 0. Soft bracket on the negative infinity, hard bracket on the 0. So it always gets a hard bracket on a value that it can be equal to. Okay, there we go. There's our inequality and interval notation. Let me just box all of them to be consistent. So I would take it either way. You could give me the red inequality notation or the purple interval notation. They both work. Let me slide up to the next one. All right, the next function here, we have 2x squared. So if I look at that 2 right there, that signals to me a vertical stretch by a factor of 2. That's usually how I write it. So a vertical stretch by a factor of 2. And what does that actually mean? It means it's a multiplier on the y values. The y values are going to multiply by 2. Let me write that. So y values are going to multiply by 2. Okay, so again, I'm just going back to what my parent function would have looked like. So here at the origin, normally I would go over 1 and up 1. But instead of going up 1, I need to double that because my y values are being multiplied by 2. So from the origin, I'm going to go over 1 and up 2, here and here. Back to the origin where my vertex is. So now I would go over 2. Usually we go over 2 and up 4, but we're not going to go up 4. We need to double it. So 2 times 4 would get us 8. So I'm going to go over 2 and up 8. And same over here. And then I can connect my dots. So this is my quadratic parent function, but it's undergone a vertical stretch by a factor of 2. So it looks skinnier than the parent function because all of those y values have doubled. The x values stayed the same. Okay, the domain, what can x be? X can be anything. For any quadratic function, we're going to see that the domain is always all real numbers or from negative to positive infinity. That will always be true. So here we go. All real numbers or negative to positive infinity, just like that. Okay, for the range, Okay, I'm reading it bottom up, so I can go 0 to infinity. My y values are greater than or equal to 0. Or negative, not negative to positive infinity, 0 to positive infinity. So 0 here would be a hard bracket, and then my infinity takes a soft bracket. Go ahead and box it. All right, next one. So here I have y equals 1/2 x squared. So right here, that 1/2, it's a vertical compression. Actually abbreviate like that. So a vertical compression by a factor of 1/2. So all of the y values are going to be multiplied by 1/2. They're all going to be cut in half. Okay, go back to the starting point for the parent. We start at the origin. There's my vertex. Normally, I would go over 1 and up 1, but instead of going up 1, I'm going to go up half of 1. Half of 1, here and here. Okay, back to the vertex, back to the origin. My next set of points, I would normally go over 2 and up 4, but instead of going up 4, I'm going up half of that. So over 2 and up 2, here and here. Let's say I want one other pair of points. Back to the vertex, back to the origin. Now we would go over 3. Normally, with the parent function, we'd go up 9. But if I cut that in half, that's 4.5. So I'm going to go over 3 and up 4.5 here and here. Okay, and then I can connect my dots. Just like so. Okay, so I should see in comparison to the parent function, it looks a little bit fatter, it looks a little bit more squished, and that's because all of the y values were cut in half. So here again is that vertical stretch by a factor of 2, and here is the vertical compression by a factor of 1/2. It's a multiplier on the y values. The y values doubled here. The y values cut in half here. All right, my domain, what can x be? X can be anything for any quadratic function. So all real numbers or negative to positive infinity. Range is different. Range is the y values. So if I trace it, I see, okay, it has a value here at 0 or anything more. So I can say that y is greater than or equal to 0. Or in my interval notation, I can say from 0 to infinity. Hard bracket on the 0 and soft bracket on the infinity. All right, two more. All right, so next up here, we see our first translation. So translations, we're moving left, right, or up, down. So when we're in the inside of the function, so inside of those parentheses for the quadratic function, that signals to us that we're sliding left or right. So it's a shift left or right. And it's always the opposite of what it appears. So right here, when it reads as x plus 5, that is telling me that it's a horizontal translation. Sometimes we call it a shift, which is fine. So horizontal translation or shift, and we are 5 units to the left. So we're taking our parent function and we're sliding every point 5 units to the left. So instead of being at the origin, we're sliding 5 units to the left. Puts us right here. So there is my vertex, and I'm building from that location. So I'm going over 1, up 1, okay, back to the vertex, over 2 and up 4. Back to the vertex. If I wanted another pair of points from the vertex, I could go over 3 and I could go up 9. So here and here. So here my parabola looks just like the parent function. Every point, though, has moved, has shifted 5 units to the left. Okay, domain, It's the same for any quadratic function. All real numbers or negative to positive infinity. Okay, my range, so if I trace it bottom up, so here smallest value is 0 all the way up to infinity. I could write that as y is greater than or equal to 0. Or I can say 0 to infinity, hard bracket on the 0, soft bracket on the infinity. Okay, last up, here we see that we have nothing on the inside. There's nothing inside of the function. There's nothing inside of those parentheses. We see something attached on the outside. So that -5 on the outside tells me it's a vertical translation, or shift, if I'm being less formal, 5 units down. So every point in the parent is moving 5 units down. So instead of starting at the origin, we start 5 units down right here. And then we build off that location. So from the vertex, we go over 1, up 1, back to the vertex. Now we go over 2 and up 4. If I wanted another pair of points, back to the vertex, over 3 and up 9. Right here and here. Okay, and then I can connect my dots, smooth out my beautiful curve, and there is my beautiful quadratic function. So my domain here, always the same, all real numbers, it's always what x can take, or negative to positive infinity. Okay, my range, right, if I trace it bottom up, I see, well, the smallest y value is at -5. So y is greater than or equal to -5. And that makes sense because we were sliding everything down 5 units. So the origin, where the vertex was, right, we're moving it down 5 units. So this makes perfect sense. And then in interval notation, we're naming it from the extremes. So from -5 to infinity, -5 takes a hard bracket, infinity takes the soft bracket, like so. All right, so this has been a little intro to graphing quadratic functions with transformations. Everything on this page had just a single transformation. In terms of domain and range, domain is everything that x can take, every value that x can take. And for any quadratic function, it will always be the same. It will be all real numbers, or in interval notation, negative to positive infinity. For the range, we're saying all the values that y can take. So in this case, we said a lot of y is greater than or equal to 0, or if it has a vertical translation up, down, or if it has a reflection, that might change. If we use interval notation, we always want to make sure that if it's a value that it can be equal to, we give it that hard bracket. If it's a value that it cannot be equal to, we give it the soft bracket or the parenthesis. All right, that's all I got for today. Have a wonderful rest of your day.